Following presentation was made by John Frensley at World's Finest Physics.
All right, so up to this point, we've talked about a lot of things that have been moving, and normally it's been in a straight line, with the exception of previous lesson where we talked about centripetal acceleration. But now we're going to look at how things move as it rotates. So our central question for this lesson is, how do we describe the way an object rotates? Our objectives, we will be able to define and use quantities of rotational motion, angular displacement, angular velocity, and angular acceleration. Some of those look familiar. We've briefly touched on it before. We're also going to be able to relate these quantities to each other through words and equations. And we're going to be able to relate these quantities to the quantities of linear motion. Vocabulary, we know kinematics is the study of motion. Translation means an object's center of mass is moving up and down, left or right, forward, backward, or any combination of these. So it's not rotating. Translational is straight line. The adjective translational is used to describe motions that are translations. Sometimes the word linear is used instead of translational. So we have translational motion. We also have rotational motion. Rotation is a motion where an object's atoms make uniform circles around a line called the axis of rotation. The adjective rotational is used to describe motions that are rotations. Sometimes the word angular is used instead of rotational. So angular, rotational means the same thing. It means we're going in a circle. Angular displacement is the angle an object rotates through. The symbol is theta. The unit is radians, or rad. Remember radians, what radians are, and remember that rad is not exactly a unit, but more of a placeholder. Angular velocity, how many radians an object rotates through every second. The symbol we use for this is omega. The units are radians per second, or rads per second. The basic equation from earlier in the year, omega equals 2 pi over the period. Omega also equals 2 times pi times the frequency, because frequency equals the inverse period. And omega equals your change in your angular displacement over your change in time. Angular acceleration, how many rads per second of angular velocity an object gains or loses every second. The symbol we use for this kind of looks like an A, but it's alpha, lowercase alpha. Units are rads per second squared. Basic equation is the change in angular velocity over the change in time, just like angular velocity, or just like regular acceleration is the change in velocity over the change in time. Remembering circular motion, this is going to be a quick review. What we know about position is where an object is located. Displacement is the distance straight from an object's initial position to its final position. Displacement has direction and magnitude. Displacement is the vector. When describing an object's position, we generally state where the object's center of mass is located. You don't realize this, but everything we've done so far this year, we have condensed into a point mass. So we've taken a car and we've not treated it like a car. Instead, we've pushed all of that mass to the center of mass for that car, and we've only been looking at that point. That doesn't take up any space. Velocity is the rate at which an object's position is changing, measured in meters per second and calculated by displacement over time. Time is the time it takes for displacement to happen. Acceleration is the rate at which an object's velocity is changing, measured in meters per second squared, calculated by the change in velocity over the change in time. An object can have as many as 2 accelerations. We have tangential acceleration, and that tells us how much speed an object gains every second. So if an object has a tangential acceleration, tangential means touching, moving in the same direction. You can think parallel in this instance. So if an object has a tangential acceleration of 6 meters per second squared, the object is gaining 6 meters per second of speed every second. Tangential acceleration is always directed tangent to the path the object travels in the same direction. If tangent acceleration is in the same direction as velocity, an object is speeding up. If our tangential acceleration is in the opposite direction, the object is slowing down. Then we also have centripetal acceleration, which is the acceleration that is responsible for changing an object's direction, causing the object to travel along a curved path. Tangential acceleration changes speed. Centripetal acceleration changes direction. Centripetal acceleration is always directed perpendicular to the path it travels, directed towards the center of the curve, the center of the circle that best fits the curve. Circular motion happens when an object's center of mass makes a circular path as it travels. An example, a car makes laps on a circular track. For rotation, the center of mass might stand still or travel in a straight line, but the atoms that make up that object are circling around the center of mass. They seem kind of similar, but they are quite different, and we handle them very differently as well. An example, a car is traveling on a straight road. Even though the car goes straight, a wheel of the car rotates because the atoms of the wheel make circles around the wheel's center of mass. It is possible for rotation to happen where the atoms make circles around a point other than the center of mass. When an object rotates, the object's atoms make circles around a line called the axis of rotation. The axis of rotation does not have to pass through the center of mass. What is that talking about? I have a golf club balanced about its center of mass right now, right? And if I move my finger away from the center of mass, it's now going to rotate around the center of mass. But if I'm holding the golf club and I am swinging this golf club and then I break my wrists like that, now the golf club is rotating about this pivot point right here where I was breaking my wrists like this. So I'm causing this golf club to rotate around an area that is not exactly the center of mass. If you drew many circles representing the paths that the atoms circle, the circles are all centered on the axis of rotation line. The axis of rotation is perpendicular to the circles the atoms make. The wheels of a car are built so the axis of rotation passes through the centers of mass. But while a door's center of mass is at the door's center, the door's axis of rotation is at one end where the hinges are. So next time you're riding in a car that's traveling down the road, look at the hubcaps of the car that's driving next to you at about the same speed. You'll see that right in the middle, there does not appear to be any rotation. Meanwhile, if you look at the outside of the hubcaps, it's going to be blurry because they're rotating so rapidly. Unless they're spinners, then everything just goes out the window. Physics breaks at that point, I think. For the door, we're going to examine that door situation a little bit later when we talk about torque in the next lesson.